In this subsection, we'll look at problem kernels, a well-overloaded term, but I'll make precise what we mean by this in this context. And that's an entirely different way to design FPT algorithms. You can think of it as a reduction rule. I'll have some simple examples soon. Think of any simple, easy wins, what to do to your input to make some parts that certainly are not helpful go away. And so the goal is not to change the outcome. If we're thinking about a decision problem, it should not affect whether it's a yes or no instance, but you're allowed to modify the instance and ideally make it smaller. And you should do this efficiently. That's the idea. So a trivial example, if we're back to the satisfiability problem and we have a conjunctive normal form that for some reason contains a clause with a single literal. Because we're taking the and of all the clauses, if there's a literal that just contains x, that means x has to be set to true. Or if it's not x, to false. There's no choice, actually. So a simple reduction rule would just do exactly that. Okay, not exactly exciting, because most formulas won't contain any such extraneous clauses. But if they do, it's a valid reduction rule. It certainly doesn't change what the truth value is. Now, this sounds super unhelpful or boring and less powerful than anything. It's actually a special case of, I guess, the most effective way to solve satisfiability in practice. Maybe this is a remark at this point as a digression. It's not part of this module, but even though satisfiability is NP-hard, is actually very tractable for many practical applications to reduce a problem to a large propositional logic formula and call a black box SAT solver to solve it, even if it has thousands of variables. And they certainly don't do the exhaustive search that we looked at before. 2 to 1,000 would never ever finish. They use some clever heuristics and based on this resolution calculus, which really is not more than that. If you have two clauses that have some literals, but they also have, they overlap in one variable and they use it in the opposite way, then instead of those literals, you can add a new literal, which takes all the parts without x, because in a way, these two clauses together mean either x is true or false. So at least in one of them, you'll need some of the other literals to become true. So you can add more clauses to your formula this way. And again, this sounds maybe not super powerful, but if you combine this with clever heuristics of how to choose these, that's exactly how practical SAT solvers work. Okay, that's just a side remark. I'm not claiming this is an FPT algorithm in a formal sense. Let's look at a different example where this is a bit easier to make the case. Back to vertex cover. If your graph happens to have vertices of degree 0, they don't contribute to anything. You just delete them. There's no edges that they would cover. And if you have vertices of degree 1, right, then there's some part in the graph, and this vertex is just dangling off here. This edge, its single edge, would just as well be covered by the other endpoint. So just get rid of this guy. It's not going to ever be part of an optimal vertex cover. Yeah, okay, I'll retract that statement, but there's always an optimal vertex cover without that vertex. This rule, again, doesn't look very powerful because many graphs won't have too many degree 0 and 1 vertices. But thinking along these lines will actually lead to something more interesting. The goal here will be, I mean, you can define these simple rules forever, but the goal is to have rules where you can prove that they leave the instance much reduced, namely so much so that it's only bounded in terms of the parameter. That's what we're really after. So I'll often say pre-processing is just anything. You do something to the input before you get going. What we're after in this chapter for a problem kernel is something more specific. Okay, let's have a look at a more refined version of this vertex cover rule. This one's a bit more clever. So we're given an instance to this parameterized problem, a graph and a threshold k. Now suppose the graph contains a degree greater than k vertex, so a vertex with strictly more than k neighbors. If I'm only looking at vertex covers of size up to k, there's no way I'm going to include more than k neighbors of this single vertex, so I have to choose the high degree vertex. There's no other option. Any vertex cover will have to use that one if it's supposed to stay below k vertices. So I might as well include this vertex, get rid of all its edges, and make k1 smaller for the remaining graph. Okay? Okay. Laptop decided to freeze. You can think about the next point. You can apply this rule simultaneously for all vertices. You don't have to apply it one by one. You can in one shot get rid of all the vertices of degree larger than k, because the reasoning will be the same for all of these. Neither of them can include all the neighbors, so you have to use all those vertices. As always with these rules, we'll think of them as doing one step, but we'll apply the rule as long as it applies. So as long as you find vertices of degree greater k, you'll apply the rule to get rid of them. The thing why this can cascade is that you're also making k smaller as you're going. So more vertices might qualify to be of high degree. Okay. Woken up again. Good. So I wanted to draw this high degree vertex, but maybe by now it's kind of clear. Let me just leave it with this. Okay, so this is more promising, maybe just because it seems to do something more interesting, and if k is not too big, this has the potential of making the graph really small. Let's first define what we want formally. So a kernelization is talking about a parameterized problem, as always. And a kernelization takes one input and transforms it into another one. And it also transforms the parameter. So there's a mapping, a new parameter if you want. I mean, I guess that's not right. The parameterization stays the same, but the result of the kernelization will have a smaller parameter. Okay, so what are the conditions? First of all, if the input is a yes instance, then it's supposed to stay a yes instance after the kernelization, and vice versa. Second, this kernelization should be efficiently computable. And third, that's the important part, the size of the output must be bounded by some function of the original parameter. And that means we're actually doing something more than just a general pre-processing. We're really producing a kernel, which is the hard part of the problem subject to the parameter k that decides the problem, and we get rid of all the extraneous parts of the problem. Okay, we call this x prime a kernel, and this mapping capital K a kernelization. The function g is often called the size of the kernel. You can already see the game that you want to minimize this size. So let's convince ourselves that this reduction we've seen before, reducing the high degree vertices, already gives us a kernelization for vertex cover. And we can even say something about the size of the resulting kernel. Well, what I mean by this is that we repeatedly apply the rule. This is important. So when we do this, after we've done this, I guess we also need to we need to combine it. Bus's reduction really is Bus's rule for high degree vertices. Together with this simple rule from before, the 0-1 degree rule. So I'm removing isolated vertices, I'm removing leaves, vertices of degree 1, and I'm applying this high degree removal rule whenever possible. But when none of these rules is applicable anymore, then I'm left with a graph where all the vertices have degrees between 2 and k. Okay? It'll probably be smaller than k. This is the original k of the input, but that's say, a worst case guarantee. Now this means whatever the vertex cover looks like in the resulting graph, if this was a yes instance, it can only contain k vertices. And so because these are bounded in degree, I can only cover k squared edges with k vertices in this resulting graph. Which also means if I have more than k squared edges, if my number of edges m is larger than this, there's no way I'm going to make a vertex cover with k vertices. So I can output, as result of my kernelization, a trivial no instance. So if you want to be specific, you can say I'm just forgetting about the old graph and I'm constructing a complete graph on k plus 1 vertices with the same parameter k, and then that's a no instance. And otherwise, if my number of edges is at most k, well, then both the number of vertices is also at most k squared, because I have to put these edges somewhere, and I can only put I have to put I can at most put k edges per vertex. So the overall input size is bounded by, say, twice that. And so that's our kernel size. Okay? So here the rules are still pretty simple, but by looking at it after you applied them to saturation, you already get a non-trivial result, namely that you can reduce any graph to something that's bounded by k squared. Okay. Now, as the last bit here, let me prove that indeed these two design principles what we've seen essentially are the same. So whenever some parameterized problem has any fixed parameter algorithm, then it also has a kernelization and vice versa. So I could really define FPT in terms of having a kernelization. It's the same thing. So it's an if and only if, so we have to prove the two directions or the two implications. Let's first go back. So we start with a kernelization. For our problem. And let's also assume I guess it's not an assumption. We assume that there is some way to decide the language. So but it might not be clear what the time is. As we had it before, we assume this technical condition that the running time bound is weakly increasing, as you can always guarantee, but it makes the proof easier. So now we have two cases or two steps. We're given some x where we're trying to check if x is in L. So first of all, we apply our kernelization. Let's call that x prime. That takes polynomial time. And also we know that the size of x prime is bounded by some function of just the parameter, where k is the parameter of our input, as always. And then the second step is we run our algorithm A on this kernel. So that decides, by the correctness of the kernelization, the answer for x prime is the same as the answer for x, so that will be a correct output. Now the question is, how long does it take to run this algorithm A? So far we've only spent polynomial time. But the time for the second step, we can only give as t of x prime. Now this is where we assume the weakly increasing, which means we can upper bound the outcome by upper bounding inside. And now this is something that only depends on k. So that's an FPT time so far, right? So these two steps together give an algorithm for the kernelized, for the parameterized problem with running time big O of this part and a polynomial in n. Let me just write poly n, or n the input size, I guess. So, which is already remarkable in itself. If you have a kernelization, you get an FPT algorithm, but you actually get one with a plus between the two parts, not a multiplicative condition. And so once we've proven the whole theorem, you can actually always go to an algorithm with this plus, because you can take any FPT algorithm with the part that you see in a minute, convert it to a kernelization, and then go back, and then you have a running time of this shape. So that proves the one direction. Now for the other implication, we start with an FPT algorithm. And we know it has some running time That's given by a function of the parameter times a polynomial. And so if that's the case, then there will be some exponent c so that this is true. Okay, this is an upper bound for the running time. And yeah, I guess we can even leave this off and claim that that's an upper bound. We can always make the polynomial a bit bigger if needed. So the trick now will be to simulate this algorithm A, but only for a certain amount of time. We give it n to the c plus 1 steps. Okay, so far that's a polynomial time because it's bounded by a polynomial. And now there are two options. If A terminates within that time, then it has produced an output. And if it outputs yes, then we're supposed to produce a kernelization. So we have to take the input and produce an equivalent instance that's small. So I'm just taking any fixed yes instance of constant size and output that. It's a bit of a stupid kernelization, but it works. It's according to the definition. It just ignores the original input because it solved it already. And if the output was no, then we likely likewise output a no instance. So the other option is that A did not finish, and we stop it after this many steps. So that means this was not enough for this time bound. But if that's the case, then we just divide by n to the c and get that n is less than f of k. Oh, look, the original input size is bounded by something just in terms of the parameter. So it's already a kernel of its own. And so in both cases, we just spent polynomial time for simulating A, doing trivial stuff. Here, also not doing anything interesting. We're just outputting the overall input before again. So maybe you feel cheated a bit by this second part because it didn't do anything smart. That's how proofs sometimes go. Still, the proof established this slightly non-trivial fact that you could have defined FPT with a plus instead of a multiplication for the part that contains the dependence on the parameter, which I think this is the only way to prove it that I know. So it's sometimes non-trivial things come out of these proofs, even if in hindsight they might feel a little less interesting. Okay, so we established that really FPT is the same as having a kernelization. And another example of kernelization we'll have to wait for next week.